cartoon here on the top right corner where you have the vapors off-gassing from groundwater and soil, potentially diffusing upward toward a building slab, can then come through the cracks through advection. And I think this is what we understand well. This is our basic understanding of diffusion by advection. You can see the vapors in the cartoon spewing through the cracks. But there is another pathway, which is diffusion through the microscopic pores of the slab. That, as Andrew alluded to as well, is driven by concentration gradient, not pressure. So that, even though it may not be as rapid as an advection through a crack, it does happen over the full bulk of a large slab, and it also happens potentially 24/7 and 365 days a year because the concentration gradient usually doesn't stop like pressure gradient might. So this is the pad sampler that we developed. It's really pretty simple little device. It's basically, think of a Band-Aid and replace the cotton part of the Band-Aid with activated carbon. And then the adhesive of the Band-Aid, the little plastic strip, replace that with an aluminum piece of tape, which about the size of a quarter. You just lay the little adsorptive layer down and then cover it with the aluminum tape. And then as the vapors diffuse through the slab, they get intercepted and absorbed by the activated carbon. At which point we can leave those deployed for a few days up to a couple weeks, depending on source strength, and then send those off to Beacon, who's developed a way to thermally desorb these wafers like they do their other passive sampling devices, and can detect down to 10 nanograms onto one of these pads. So this is the little pad sample. So I'm going to skip to diffusion theory right now so we can talk a little bit about theoretical calculation of flux through a slab. So diffusion through concrete basically follows fixed first law of diffusion, which is shown here in this equation. It's a differential equation, but it's actually a pretty simple one, and it gets even simpler when you realize that indoor air is basically negligible compared to the subslab, typically concentration-wise. So then the fixed first law really reduces to a simple four-term equation where the flux is equal to an effective diffusion coefficient times the concentration beneath the slab divided by the slab thickness. It's pretty straightforward, but the nut to crack here is, what is the diffusion coefficient that we use for calculating theoretical amount of diffusion through a concrete slab if we know the subslab source strength? Well, what we started digging around, we found that the Johnson and Edinger model is actually a pretty good theoretical basis for this. There's an equation that's part of the J&E model for diffusion. You could use this for soil, but you can also use it for concrete. And if you just use the default parameters that are provided in the EPA Visual Workbook for the chemical properties, and then go to the literature for some values for the air and water-filled porosity of concrete that we found. You plug all that into the equation, and you come up with a diffusion coefficient for concrete of about 1.1 times 10 to the minus 4. And what's really interesting is this equation for soil, which we use to calculate diffusion through soil with the J&E model regularly. The default parameters for soil come up with a diffusion coefficient that's only 15 times more than this. So, we don't think of soil as being a good barrier to diffusion. And if cement's only 15 times less permeable, then I don't know if it's exactly going to be a good barrier either. But we'll see some data here in a minute. So to apply this theory, we looked at a good large warehouse building where we had a good robust data set beneath the slab. You can see all of these triangles here are passive subslab samplers, Beacon samplers that we install by drilling through the slab. The slab is big. It's over 100,000 square feet in size. and robust too. It's pretty thick, almost 10 inches thick on average. So we use this data set and that diffusion coefficient I just showed you, we calculated, well, what's the flux through this building? And so taking each one of those points and then dividing the area around it by a Thiessen polygon, so then we can multiply each concentration point by its respective area, sum them up, and we can get the overall predicted flux through this slab. And when we do that, using that simplified Fick's law, we got about 250,000 micrograms per hour flux into this building slab based on that robust subslab data set for subslab. So that seems like a pretty big number, 250,000 micrograms per hour when we measure things in micrograms per cubic meter, usually in indoor air. So we'll see how that comes out later in the presentation. But for flux, really, we want it on a per square meter basis. So when you divide this by the total building footprint, you get that the flux that we measure, or theoretical flux into this building, was 23.4 micrograms per square meter per hour. So how does that compare to what we did when we put the pads down to actually measure the flux and compare to that number? So what we did was we installed essentially 4 pads at 14 different locations in the building, and you could see the squares that represent where those pads got installed on the slab. There were 2 areas where we did grids of 3 by 3 and a 1-foot square to look at variability within that small area. And then we averaged that grid down to 1 point, and that's what we applied in each one of these, area A and area B. So with these 14 points then, again with the Thiessen polygons to divide up the area, sum it all up, we got a flux of 225,000 micrograms per hour. So this is measured flux now through the pads, which was quite similar to the flux I showed you earlier. And then if you divide that by the area of the building again, the per square meter flux was 21 micrograms per square meter per hour, which was remarkably close to the Fick's law calculation. So, I mean, what that says is, well, we used that diffusion coefficient from J&E worked really well. It came out to be a good representation with theoretical flux of what was actually measured. And another interesting thing you can do, if you know the flux in through the floor of a building, you can calculate the predicted indoor air concentration if you know the air exchange rate of the building and the building geometry. So using this equation here and that flux result of 21 that we measured, we calculate, given the air exchange rate that we measured using a blower door, a 40 was our predicted indoor air concentration from the flux through the slab that we measured. And we collected 2 indoor air samples during the pad's deployment. And when you average those 2 samples, the average air in the building was 39. So what this is saying is that the flux, the diffusion that we measured through the slab actually counted for all of the indoor air in this building based on our assessment. So diffusion for this warehouse in particular appears to be predominantly where the mass is coming into the building. I mean, it does have some cracks and gaps, but I think, you know, they're fairly negligible, and they were not significant relative to diffusion. So overall conclusions, you can't overlook diffusion. You really got to take a close look at it. Depending on your building, it might be more significant than you might think. The little pads were quite effective at measuring the flux, and it does appear that they're measuring what we expect to come through. And with a mitigation system, you know, like Andrew mentioned, if negative pressure may not be the only thing you need to mitigate a system. You might need to flush out underneath the slab to break that concentration gradient. And you could use pads as a tool to, before and after you do a mitigation design to see effectiveness. So with that, I'll turn it over.
Awesome. Thank you very much, Michael.